what caused this increase? Tension or compression? Tension. So tension is considered to be positive. Compression is the opposite, as you said correctly. So that's why it's minus 172 megapascals. Okay, so we can write that delta L divided by the length at room temperature is equal to the thermal strain, and that's equal to the thermal expansion coefficient times delta T. Heated temperature minus the original temperature. And what we're going to do is the same trick or the same process that is used in mechanics, because this is a statically determinate problem. We remove one of the supports and we'll let it expand by the amount of delta L. And we can calculate that. How can we calculate that? If there was no constraint, you heat something up, it expands. And then what we do is after it was extended, we come back. So it is constrained between the two steel plates. It's not allowed to move. We remove one of them and heat it up. So it does expand. It does expand by however much. Then what we do is we come back and push it back to the position of that second steel plate. All right. So I understand that if you're industrial, you're not taking mechanics solids, but this is a trick. Does that make any sense? Okay. In mechanics or in general, this is called a kinematic condition. And statically indeterminate means that we cannot solve it just based from statics. Because what you can say that the force or the stress on both sides is equal to the one that's in the material. We cannot separate the forces, so we need another compatibility equation. And the compatibility equation comes from the fact that it does not move. Funny enough, right? They call it kinematic condition. Nothing moves. Sometimes there could be a gap. Okay, so it could be like a millimeter gap between the steel plates and the whatever you're heating up. And then it would extend by that 1 millimeter and hit the wall. And once it hits the wall, it doesn't move any further. So you would account for that 1 millimeter in your analysis. So we can write that the compressive strain is equal to the minus delta L over L, and that's equal to the minus thermal strain. Okay, they work against each other. So what the material wants to do when it is expanding becomes longer, right? So that part, even though it is heated and it expands, we treat it as tension. I want you to follow the logic. So we treat it as tension, it expanded, and then I come back and I push it back to its original dimensions between the two steel plates. So we can write that the stress is equal to the elastic modulus times the compressive strain. And we put all those equations together, get minus the elastic modulus times the thermal strain, so minus C times alpha L, this is thermal expansion coefficient, times delta T. And then we need to solve for the temperature. This T sub F is how hot it needs to be, right, from this equation. So we get T0, which is room temperature, 28 degrees centigrade. It needs to be a space in here, minus sigma, which is minus 172 megapascals, because it is in compression. That's what's given in the problem, divided by the elastic modulus, which is 100 dPa, divided by the thermal expansion coefficient, which is 20, times negative 6, 1 over degree is the thermal expansion coefficient of brass. And you can look it up in a properties table. So this is kind of like a mechanics and materials combined problem with thermal expansion. Do you have any questions about this example? Do you like tea? Do you drink tea? How do you make tea? How do you make tea? Heat up water, tea bag. Does anybody use something that is not tea bag or not a mug, or has a special device for making tea? Anybody? Okay. Do you have an experience where you had something made from ceramic glass and you pour hot water and it cracks? Have it ever happened to you? Yes? What happened? Do you know what a French press is? What's a French press? Yeah, there's a little plunger, so you can make coffee or tea or whatever you're brewing, right? IKEA sells them for cheap. It's a European thing, right? You can take coffee or you can take tea, put it in that device, right? And then you pour boiling hot water in it, correct? Okay, that's when this thing can crack. And that's what we're going to talk about. I actually considered bringing the stuff and making an experiment, but I don't want to make a mess. But imagine, like, you can take a glass rod, and you can take a lighter, and you heat it up. You hold it with something so that you don't burn your hands because of the thermal conductivity of glass, right? You cannot just hold it. You heat it over here. You'll eventually burn your hand, right? So you need to have some thermal insulation to hold it. And then you put it in cold water. And when we put it in cold water, I can show you a video, I guess. Just to show you what happens. How long is that? 2 minutes, okay. Sound?
The American Ceramic Society and the Ceramic and Glass Industry Foundation are pleased to provide you with this instructional video from the teacher-led demonstration of thermal shock. The objective of this lesson is to illustrate thermal shock and the effects of differing amounts of modifier on the properties of glass. In this demonstration, 3 different types of glass rods will be heated so that students can observe the amount of thermal shock that occurs. Some of the materials used in this lesson are included in the Materials Science Classroom Kit, while other items will need to be purchased. Those items are commonly found in grocery or department stores. In some instances, it is appropriate for students to bring some items from home, which helps pique their interest. The materials needed for this demonstration are 3 soda lime glass or flint rods, 3 borosilicate glass rods, 3 fused silica or quartz glass rods, a torch head, a small propane tank, ice water. While you are setting up, have the students record their observations during the demonstration. Show the students the difference in color of the 3 glass rods by looking at the ends. Attach the torch head to the propane and turn on. Heat one end, about 1 inch, of the soda lime glass rod in the flame. Try to hold the glass rod so that the same length of glass is in the flame throughout the heating. Point out the sodium flare that occurs as the glass heats up. Allow the glass to sag or slump to show softening. Remove from the flame and quench in the ice water. Thermal shock will occur and pieces of glass will break off onto the bottom of the beaker. There will be many fractures throughout the portion that was heated. Heat one end of the borosilicate glass rod in the flame, keeping about 1 inch of the rod consistently in the flame. Sagging or slumping should be harder to achieve, but the end should fire polish, become smooth or polished. Some thermal shock will occur, but there should be fewer overall cracks than with the soda lime glass. There should be 1 or 2 cracks at the interface between where the glass rod was in the flame and where it was not. Heat one end of the fused silica glass rod in the flame in the same manner as the 2 previous rods. There should be no sodium flare and no sagging, slumping, or fire polishing. Remove from the flame and quench. The rod will not thermal shock and no cracks should occur. Consult the teacher's manual included in the Material Science Classroom Kit for discussion questions to ask before, during, and after the demonstration.
Okay. What did we see? It's a good example of the motto of the class. To control the process, to control the structure, to control the properties. Those three different glasses, if they were not labeled, you probably may be able to tell the difference if you look at the edge, but maybe not. So there were three types of different types of glasses with different edges that we discussed during the ceramics. So let's consider what's happening. The rod was heated up, and for a small diameter rod, you can assume that the temperature was constant throughout. Correct? Now what happens once it was inserted and placed in the ice cold water? The temperature dropped, but did it drop through the whole volume? Where did the drop of the temperature start? From the edge, right? And eventually propagated to the center. And it took some time. So, what is the difference in the temperature? On the skin, the surface, versus inside? Obviously, the one on the surface is going to be colder, right? And what happens to the materials when they are subjected to lower temperature? Do they expand or do they contract? They contract. So you have the surface layer that wants to contract. It wants to shrink. But the core is still hot at that particular moment in time. So what kind of stresses are developed on the surface? Tension or compression? See, many people get this backwards. Can somebody explain to me why the surface, when it's cooled and it's at lower temperature than the core, is under tension? I'm going to do a demonstration. See this piece of paper? We're going to go over it in a minute. But let's say I have this piece of rubber, right? And I'm attaching this piece of rubber to this piece of paper. Okay. What is the stress in the paper and what is stress in the rubber right now? We're not under stress. Okay. So imagine I'm taking this and I'm stretching it like that and I'm attaching it here. And once I attach it, what does the rubber want to do? Go back, which means it wants to compress. Okay, but what is this piece of paper doing to the rubber? Is it compressing it? No, it's putting it in tension. So whenever you try to figure out the sign of the stress, remember me and remember this rubber band. What do you need to do the rubber band to achieve whatever the configuration is? So again, it's counterintuitive. The skin layer wants to shrink. Okay? If I stretch this and I attach it to this piece of paper, what does it want to do? It wants to shrink, to relax. Okay? So what kind of stress is in the skin layer as a result? It's tension. You get it? Try it. The inside is this piece of paper. The outside is this piece of rubber. Okay? And I'm stretching it. And it doesn't matter what causing this shrinkage. This is shrinking here, right? Okay. But because it is attached to the substrate, what is the substrate causing to this rubber band? It's not compressing. It's not compressing. It feels like it is, but it's not. It's the opposite. It wants to go back. But this is keeping it from going back. So if you look from, it's all about an observer. You are the paper. What are you doing to this piece of rubber when it's like this in this situation? You're stretching it, and stretching is tension. Do you get it now? Okay. Does everybody get it now? It's important. It's very easy to get things backwards. But this is good, because at least we can have a discussion, have a demonstration. Okay, so we established that when we have this rod heated up and stuck into the ice cold water, it's under tension. Tension is equal to minus the elastic modulus times the thermal expansion coefficient times delta T. And then we're going to get these two temperatures said to be the same. So quench rate versus the sigma F over E and alpha. So alpha is the thermal expansion coefficient. So we're going to set this quench rate when fracture happens being equal to the thermal shock resistance, TSR. And you can see from this equation that it is proportional to the fracture stress of the material times K over E over the thermal expansion coefficient. This is the idea of preventing the fracture. You can see what's in the numerator, what's in the denominator, and looking at that experiment, 3 different types of glasses. One produced severe thermal shock failure, the other one was in between, right? It was just only one crack, and the third one did not. Here's another example of controlling the process, controlling the structure, controlling the property. Process is your formulation of the glass. Structure is because those network modifiers did modify it. Soda, lime glass was giving you this orange kind of lemon color when they were blowing a torch over it. Have you seen shuttle? Have you been to the Space Center, in Kennedy Space Center, or there's one in Alabama? And have anybody seen a shuttle? Sometime where? In DC? Kennedy Space Center. Okay. And what is a shuttle? What was the idea? It's called shuttle orbiter. Why is it called orbiter? And then do what? Come back. The shuttle was supposed to come back. Anybody interested in the space program? Why is Elon Musk involved and all that? My department was just, we added the aerospace, so it's mechanical and aerospace engineering now. There's a lot of stuff, a lot of junk in space. And once those launches were done, primarily by the United States and the Soviet Union, all the junk stays there in the orbit, just circles the Earth. But Earth has atmosphere. And how do they descend the rockets these days? When it falls down, there's friction between the air and the space object. Have you ever seen a meteorite fall? You realize that meteorite can actually reach the planet and cause a damage to your house or hit somebody? What are the odds of that? but it happened. So you have this thing that goes in and enters the atmosphere, and the nose is experiencing 1600 degrees centigrade. There was a need to protect it so that it doesn't burn. Because there are people inside and equipment and all that, right? And the solution was to place the tiles that provide thermal protection. Can somebody tell me why it was a tile, in the form of a tile, and not just continuous? So it can expand and contract if needed, and so that you can replace it. Okay? And some of them would fall off during this very violent procedure. But what it really is a 90% porous silicon fibers. And you can see the structure. This is 100 micron. It's basically nothing. I wouldn't say it's nothing. But this system provides very good thermal insulation.
Here are 25 key points about aerogels, drawn from the provided sources. 1. Aerogels are described as a special class of nanostructured, highly porous materials. 2. Despite their name, aerogels are solid, rigid, and dry materials. The name comes from the fact that they are produced from gels. 3. They possess unique features such as high specific surface area, very low density, often described as 95% air or ultralight weight, hydrophobicity, low thermal conductivity, and optical transparency. 4. Aerogels have a three-dimensional, highly porous structure, often composed of spherical particles fused into clusters forming almost fractal chains. 5. The pores in aerogels are typically just under 100 nm. 6. While silica aerogel is common, aerogels can be made from various materials including carbon, metal oxides, synthetic polymers, and biopolymers. 7. Aerogels are produced using sol gel technology, a method involving precursor preparation, aging, and drying. 8. The drying step of the gel is considered the final and most critical step in the production process of aerogels. 9. If the liquid in the gel is allowed to evaporate naturally, ambient pressure drying, capillary forces can cause the gel network to collapse, resulting in materials known as xerogels, which have lower porosities and significant shrinkage. 10. To prevent the collapse of the gel structure during drying, techniques are used to minimize surface tension within the pores. 11. One primary method to avoid capillary tension is supercritical fluid extraction, where the liquid is removed above its critical point where the distinction between liquid and gas disappears. 12. The first documented aerogel was created by Samuel Stevens Kistler in 1931 using a process known as supercritical drying. 13. Another drying method that avoids capillary tension is freeze drying, lyophilization, which involves replacing the liquid with gas by sublimation along the sublimation line. 14. Supercritical drying can be carried out at high temperatures, HDS-CD, or lower temperatures, such as the Hunt process, LTS-CD, which typically uses liquid carbon dioxide after a solvent exchange.
You realize this is an AI-made video?
Yep.
11 months ago. I can make a much better video now. But there's an experiment. Flame. Yeah, let me get this. How long is this? 13 minutes.
This is the ultimate test of aerogel. I put myself on the line to see who wins in the battle of flamethrower versus aerogel.
bottom line is that
So if you really want to see the insulating properties of aerogel, you gotta put it to the test.
Más campero por menos dinero. Pollo campero.
What does it look like from the back? Yeah, that's what it feels like. Feels warm. What about the other side? How hot's the other side? So this flamethrower was producing over 660 degrees Celsius on this side. Meanwhile, on the other side, we were just measuring about 50 degrees Celsius. We're going up to the highest range that this camera can do, up to 2,000 degrees Celsius.
okay.
We're not going to be able to see much except for the really hot stuff.
All right. Oh, good question. I don't know. Expensive enough? It depends how much. Installation. We talked about heat capacity, coefficient of thermal expansion, thermal conductivity, and thermal shock resistance. Heat capacity has to do with what? Can you describe to me in layman terms? Heat capacity. You heat something up, and then it exerts the heat. And the question is, how much heat is going to get exerted and at what time? Right? What about thermal conductivity? Because this is another property. How well does it conduct heat? Do you remember I said I would probably be careful, but they touched that rod on the other side and they were able to heat the other end and didn't burn themselves? So the glass is a good thermal insulator or not? How many of you bake? Anybody? What do you use? Made from? Anybody use glass? Pyrex glass, so that's a special type of glass. When you take it out, do you just touch it with your hands? Okay. We talked about thermal shock resistance. Did I do a good job explaining to you the tension versus compression? Did you get it? You sure? Okay. Okay. You asked me for the exam, right? Did you? Okay. And you realize so today's what, Thursday? The
Yes.
exam is a week from now. Okay. And what did I tell you? That I will tell you what chapters and I will tell you what problems, right? And I've been thinking about it, and I don't have the final version of the exam. So, but this is what I'm going to do, and I love it because I'm modifying student behavior. You know how? I'm going to give you. I don't know what problems I'm going to pick, so I'm going to give you more problems than are going to be on the exam. How about that? You want to know?
You lost me.
Okay. Huh? What I mean is the exam is 5 problems, 4 core and 1 extra, and now I have 7 problems.
What?
So I can go all over 7 problems, which means that you're going to try to do all of them, right? But only 5 of them are going to be on the exam. Isn't that cool? You like it? Okay. Do you like it?
Wait, Wait, is it 5 problems or 7 problems?
Say what?
How many problems are there in an exam?
The exam is going to have 5 problems. It's going to have 4 problems that are worth 100 points, 25 points each. There'll be a bonus problem worth 10 points. And I thought that I should bust my ass and make it finalized like before this class. But then I thought about it, and I'm doing exactly what I'm doing. I'm giving you more problems than are going to be on the exam. So you'll do extra 2 problems. And I can guarantee you that you're all going to do those extra, you're going to do all 5 problems, right? What is that supposed to mean? A yes? Okay. That's a yes. All right, so one problem is about chapter 9, it's about phase diagrams. You're given a weight of an alloy, and you're given a composition of that alloy. And that alloy is cooled to a temperature just below the eutectoid temperature. And by me saying that it's eutectoid temperature, you could probably figure out what alloy it is, but I'm not telling you. The first question, A, is how many kilograms of proeutectoid phase would form? Question B, how many kilograms of eutectoid phase would form? And question number 3 is asking how many kilograms of another phase would form? Have anybody figured out what the system is, what the alloy is? No? Okay. Fine. And ringing the bells? What bells? The right bells or the left bells? Okay. Any questions about the first problem? Eutectoid. First question is how many kilograms of proeutectoid, I'm not going to tell you the phase, but there's proeutectoid phase. Then there's eutectoid phase. And then a third type of phase. Like all in kilograms. Another question is about chapter 10. There's homogeneous nucleation of a metal. And you're given latent heat of fusion and surface free energy. And you're given the melting temperature. And the first question is asking to calculate the critical radius for the supercooling, and it gives you the temperature. Solidification happens by nucleation and growth, right? And if the nucleus is less than a certain diameter, it's going to get redissolved due to the surface energy trying to collapse it, or it will grow due to the increase of the internal energy. And there's an equation that balances the two. So figure out what equation. And the second question is to find the rate of this reaction, assuming that it obeys Avrami kinetics, and you are given the values for the Avrami constants. And the time is in seconds. So like next time you're going to have a party, and you're making ice, make sure you start ahead of time. So you don't call your buddy and say, hey, grab some ice. The water doesn't turn into ice instantaneously, right? It takes time. So the same thing here, this phase transformation takes time. Okay, another problem is chapter 12. The problem is about three-point bending. And you're given the geometry of the sample. And you're asked to find flexural strength if you know the load at fracture. That's the first question. The second question is to calculate the fraction of lattice sites that are Schottky defects at 800 degrees centigrade or so, and you're given the energy of the defect formation in electron volts. Another problem. It's a large particle composite, so it's like chapter 16. You have the volume fraction of the particles in the matrix. You're asked to calculate the upper limit of the specific stiffness of the composite, and you're given the data for the materials of the particles and the materials of the matrix. Another problem is dealing with chapter 18, electrical properties. You have a wire, and you're given a diameter of a wire, and you need to make sure that it does not exhibit resistance higher than a certain value, and you're given electrical conductivity. And you're asked to calculate the maximum wire length. So it's similar to example problem that we've done in the lectures last time.
Can you read that again?
You have a wire made from a certain material, and you're given the diameter of the wire, and you're given electrical conductivity of this material. You need to find out how long this wire can be so that its resistance does not exceed a certain value in ohms. Another problem from chapter 16 is dealing with aligned fiber reinforced composites, and you are given a tensile strength of that composite. The question is calculate the volume fraction of the fibers that will be necessary to and you're given the average fiber diameter and the length. So you need to calculate the volume fraction to get this property, which is the tensile strength. And the second question is, you're given the fracture strength of this fiber, and you're also asked to calculate the volume fraction of the fibers that would be necessary. And the third one is the fiber matrix bond strength is given, and then based on that you need to calculate the fraction, volume fraction of the fibers. And question number 4 is giving you the matrix stress at failure, at fiber failure, and you're asked to calculate the volume fraction of the fibers. Man, you're going to become experts in composites. But you've done this problem during the last session, right? You've done composites on Friday? I was there, I saw it. Last time it was like 5 people who attended the help session. Make sure you show up tomorrow. You know why? It will help you. I'm happy to see so many faces. I'm really happy. Because it was like, and I guess I'm competing with other classes, right? When it gets closer to the exam, you guys show up. Okay, and another question deals with chapter 14, polymers. You're given the weight of the molecular weight and the ranges. The first question is asking to calculate the number average of the molecular weight. The second question is asking to calculate weight average molecular weight. And the third one is giving you the degree of polymerization. And you're asked to find the repeat unit molecular weight. I can tell you that the TAs have very, very good impression of you, thinking that you can solve that. And you can, because I'm telling you what you're going to be solving. But, yes?
From back to question 3,
You speak up.
From back to question 3, there's just some gaps, like some things I didn't hear. I know you were.
Which one was question 3? Question 3?
Chapter 12.
Okay, yeah, there's a 3-point bending that's performed on a specimen, and you're given the geometry of that specimen. Diameter and the width, to be exact, and the distance between the supports. You need to find the flexural strength if the loaded fracture is equal to so many newtons. And the second one is asking to calculate the fraction of lattice sites that are Schottky defects for a hypothetical ceramic at a certain temperature. And you're given the energy of the defect formation, so in electron volts. So these are 2 different problems. A and B, yes?
What about for the homogeneous nucleation one? I wasn't able to catch that.
Homogeneous nucleation.
Yeah, question 2, chapter 10.
Yes. What's the question?
Could you repeat it? I didn't understand.
Okay, all right, okay. There's solidification of a material. And so it goes from liquid to a solid. And it's this nucleation is homogeneous. And you're given latent heat of fusion and surface free energy. And you're given the melting temperature. The first part is asking to calculate the critical radius for the supercooling of certain number of degrees, temperature-wise. And the second one is asking to calculate the rate of the reaction, assuming that a base Avrami kinetics, and you're given the constants n and k for the Avrami kinetics. And time is expressed in seconds. And I think it's fair for a week, but I'm not going to use all the problems. Actually, I know which problems I'm going to eliminate now, but I'm not going to tell you. Yeah. Only worth 10 points. I mean, the idea is that you're earning the points. I'm not just giving out freebies. Okay? Good? Yes?
I know it's like further on, but questions 4 and 6, they were both for chapter 16, but especially for question 6, which had 4 parts, there's a lot of misinformation.
First of all, there are no assigned numbers. These are just problems that are random. Chapter 16 is dealing with fiber reinforced composite, and you're given the longitudinal tensile strength. And all the questions are asking to calculate the volume fraction of fibers that would be necessary. And the first one is to achieve this kind of strength in the composite if you're given the diameter of the fibers and the length of the fibers. And the second question gives you the fracture strength. And the third question is giving you the bond strength and the matrix stress at fiber failure. This is not an easy problem. To solve it, you need to really get to understanding what I just said. But I like it. Who wanted a $100 gas coupon? $200 gas? Was that in another class, right? See, you all wanted Chick-fil-A coupon for $10. That made no difference in mechanics. They were not excited about it. One person said, I want a $100 gas coupon. I said, I'll give you 200. People get motivated by different things. Any other questions? What I may do, and once I'm going to finalize this on Tuesday, like next Tuesday, I told you I have the subpoena for the court. That's hearing is at 1 o'clock. So I'll show up and tell you what the exact problems are going to be. How about that? But in the meantime, I gave you 7 problems instead of 5. Is that fair? Okay. You asked me to do something for you. I ask you to do something extra for yourself. Right? Do you like this kind of? There's a you know what the term is, or what people say? You cannot push on a rope. You know what that means? I cannot push on it. I can only pull. So that's the idea. I can indirectly control your behavior by having, like another faculty in my department, by having a mandatory quiz every lecture, and those quizzes are worth 90%. And guess what? All the students show up. And I don't know if I can be good enough as Diana Ross to have the full house, or Gypsy Kings. You know what I mean? I try, but I'm only human. Now, do you want to see something cool? I want to show you something really cool, or I think it is cool. I bought this on eBay before the price of the magnets went up. And I'm going to set this here, and I'm going to see if I can do this camera on a thing, and if it's going to work or not. Stop cam. It seems like it's working. And I'm looking at, something. Is it automatic? Okay. So what you see here, we don't see, is our 4 magnets. And this thing is levitating. It's levitating. It's pyrolytic graphite. You see that? So the magnetic field of this 4 very strong magnets, I'm making sure that I'm carrying it in the pocket that's opposite to my wallet, because if I bring those magnets close to my wallet, my credit cards wouldn't work anymore. Okay? And I'm gonna sit it here. The ones that are close, you can actually see that it's levitating. No energy required. Okay. This. Have you ever played with magnets? What's a magnet? When you travel, do you have magnets on your refrigerator? You do? Who does not have magnets on their refrigerator? Who has a refrigerator that you put a magnet to it, doesn't hold that magnet? And why? Magnetic material, which sometimes can be stainless steel. Is your fridge stainless? And you attach the magnet, so don't bring him magnets from Rome and Italy and other places, because it's, he's going to give it as a gift to somebody else. Ah, okay. All right. So before we dive into this, I want to ask you this question: is why is it not sticking to the front of your fridge? Because the front is made from stainless steel, non-ferrous. But the sides? What are the sides made from? If it is magnetic. It still can be stainless. There's some stainless steel but if you have steel and it's not magnetic, you put a magnet to it and nothing happens, that's definitely stainless steel. Right? So the fridge they sold you as stainless steel is just the top, the front side, not the sides. Probably the sides have a coating on them. Okay. So we will talk about magnetic properties to control the process, to control the structure, to control the property. And we will try to explain why some materials are magnets, and we'll classify them. We'll talk about magnetic memory and how it works, and we will talk about superconductivity and how the superconductors behave. When I heard about this first time was probably 6th grade physics class. And what I did is I took a nail and I took some copper wire and I wound the wire over this nail and I hooked it to a battery. And then as things progressed, I made this coil with enough turns. And that was the time when I was playing with that multimeter that I burned, so I learned so 6th grade, how old was I? 12? Anyway, I ended up taking this and plugging it into the outlet. And it worked, but it was a very strong magnet. Okay? Do you see any wires going to this? No? How does that work? Compared to the coil that I would just plug in there. In vacuum, we can create magnetic field by passing current through the coil. Okay? And it's denoted by applied magnetic field, H. And B0 is the magnetic flux density in a vacuum, which is reported in Tesla. Anybody drive Tesla? Why do they call it Tesla? I mean, this magnetic flux density. After Nikola Tesla. Why do they call the car Tesla? Boogie, 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 yeah. Well, not because it's electric, but because it has something to do with Tesla, so it's an electric car. But you can see some parameters here that are important is the number of turns. It's the length of each turn in meters, and the current that we're passing through. So we can calculate the applied magnetic field as the number of turns times the times the current divided by the length of each turn. And we can calculate magnetic flux density of a vacuum as mu times H, where mu is the permeability of a vacuum, which is expressed as 1.25 10 to the minus 6 Henry per meter. Henry is another unit. But the bottom line is that if you take a coil and you turn it like this, and you make many turns, and you supply the current, then there will be some magnetic field generated. Now, the next step is to put some material in there. And have you heard about induction? What is induction? Do you remember, do you know? Or can somebody tell me what induction is? How many of you have an induction stove? None of you? You used to have one. What happened? You cannot do what? You need to use a special pan. Okay. What's stopping you from buying those special pans? And now you're what? Using your fingers or what? Like, what do you use now? Okay. Was that induction stove installed, or did you buy it separately and it had two, what do you call them? Areas, two zones? Oh, okay. So you moved into the place that had an induction stove, and you moved with your existing pans, and you couldn't use them. Okay. Why he couldn't use them? Because we're going to answer the question of what is induction. And I'll tell you why it's worth buying those pans once you get a job and make more money. Yes? Yes, it's only heated when you have a specific metal. So the metal heats up by the process of induction. And if the metal is different, then it doesn't heat. Right? So you say, oh, it doesn't work. You just need to have a special metal. Who has an iPhone of the latest version? Anybody? 16, 17? You do. How do you charge it? Oh, look at that. What do you have attached to it? Oh, look at that. I love it. Is there a wire that goes from the first look? How's the battery held? Man, if you can afford that, you can buy some pants, man. But seriously, like, look at that. How does that battery attach? Magnet. There's a magnet. And how is this battery charging the phone? Induction. What's induction? There's a coil, and look at your case. Show us your case. Show everybody your case. Do you see that my case is different because I'm not using induction charging? I'm going to have that's my case, but there's no this ring. Okay, so you know what that ring has? There's a magnet, there's a coil in there, so that you can use induction to charge your phone without contact. What is it called? MagSafe case? Yeah. And if you have a Tesla, anybody have driven a Tesla at some point? Nobody? You have to have your phone. If you don't have your phone, it will open if you have a special card. So you have to like really change your mindset, but then you place your phone, and if it is a phone that has this technology, it can charge without any contacts. Okay, but induction is the generation of current in the material, and through the process of induction, you can step up the voltage or step down the voltage. Like, you can have one coil here, and you can have another coil here, and you connect. You're not connecting, you're putting a cord through them, and by passing the current in one coil, you're generating the current in another coil. And that's the process that's called induction. Right? Okay. So, this permeability here is dimensionless because it is compared to the permeability of vacuum. So magnetic induction is happening inside this material when you're applying magnetic field, H. And the magnetic field you can calculate from this formula. So to charge that iPhone, some engineer at Apple had to run those calculations to see how much current is going to go through this, and if that's going to be enough to charge a phone, and what time is it going to take to charge the phone. It's much easier to transfer electricity by a physical connection. Cheaper and easier, but this is fancier because you're not attaching your battery to the phone. It's pretty cool, right? Okay. If we plot the magnetic field versus magnetization, or magnetization versus the magnetic field, we plot V over H. The magnetization M is equal to chi sub M, which is the magnetic susceptibility, times H. And then this B is equal to mu 0 H plus mu 0 M. Mu 0 is the magnetic permeability of vacuum. And then this is the straight line for vacuum where H sub M is equal, X sub M is equal to, actually it's chi sub M to be honest with you, is equal to 0. And then we're comparing how the material is going to behave compared to vacuum. If that chi is going to be higher than 0 or less than 0. And this chi is a measure of the material's magnetic response relative to vacuum. Does that make any sense? You may ask, where is this magnetic thing coming from? Like, why is it a magnet? It has to do with the magnetic moments of the electrons and the spin of the electrons. Remember, the electrons have a spin? Here's the nucleus, and this is an electron. So, for the net atomic magnetic moment, it's the sum of all the moments of all of the electrons. And if somebody asks, what is participating in this magnetic thing? The answer is what's responsible in an atom for exhibiting any kind of magnetic property? Electrons and their spin. It's pretty easy, but you probably hear it for the first time. Am I correct? okay? And we say here that there are 4 types of different responses. And if we plot B in Tesla versus H in ampere terms per meter, here's our vacuum where chi is equal to 0. And then if it's below vacuum, that material is diamagnetic. And then it's above vacuum, it's paramagnetic. And if it's way, way, way up there, it's either ferromagnetic or ferrimagnetic. Sounds like 2 Italian guys. So, again, the reason some materials exhibit magnetic properties, and we're going to see how they're exhibiting them, like lack of properties is also an exhibition of properties. It's compared to the vacuum. Less than vacuum, diamagnetic, higher paramagnetic. A lot of magnetism is ferro or ferrimagnetic. Diamagnetic, what? What do we have here? Al2 or 3, or aluminum. What class of materials is that? This is what? Aluminum oxide. What is it? Is that a metal? It has a metal. Aluminum is a metal, but is it a metal? Is it a polymer? What is it? It's a ceramic. Okay, then we have copper, copper and gold, and they are what classes of materials? Copper and gold? They're metal. Silver and zinc? Also metals. So you can see that we discussed it. To control the process structure properties, we started with 3 classes of materials: metals, ceramics, and polymers. We can see that the magnets are, or non-magnets rather, ceramic and metals, paramagnetic, aluminum, chrome, moly, sodium, titanium, zirconium. These are all what? Metals. And then we have ferrite, which is a phase in iron carbon, cobalt, nickel, whatever that pronunciation of that element is, neodymium, rare earth element. And then ferromagnetic is iron oxide or nickel iron oxide. Iron oxide is, based on our classification, is what class of material? Same as aluminum, it's ceramics. So you can see that ceramics can be either diamagnetic, they have properties of less than vacuum, or it could be ferromagnetic. Yes? Let's consider this, what happens to these different 4 types. We apply magnetic field. And how's the magnetic field applied? We take that coil, right? We hook it up to the source, and we put that material inside the coil. That is how the magnetic field is applied. Right? Right? And then we see what is happening. Because the magnetic field is affecting the material. They could be, the domains could be opposing, they could be aligned, or they can be random. And that is what determines the magnetic response. Oh, the class is over? Okay. We'll continue.
Ow.
Have a look at this when you pass by. I want you to make sure that you see that it is actually levitating. It's pyrolytic graphite. careful. And this one